I've already mentioned the fact that the Graham-Schmidt process that we use in theory to derive the QR factorization is in fact an unstable method if you implement it in floating point arithmetic. So the stable alternative to that proceeds much like LU factorization does, except with orthogonal matrices. So remember with LU, we produced a sequence of L matrices that we multiplied with on the left, and each one was designed to put zeros into a particular column, so that by the time we had multiplied through by all the L's, the total matrix that was left was upper triangular. Well, now we do the same thing, but instead of L's, we have Q's, and the Q's are orthogonal. So here's a little cartoon of that. Suppose A starts out as a 5 by 3 matrix. So I'm just using X's here to represent numbers. They could be anything. It doesn't mean that they're all the same number. Now Q1 is going to be designed in such a way that when we multiply by Q1 on the left, we put zeros into the first column where we want them. Everything else gets changed, but not in a way that does any zeros anywhere in particular. Okay, so after that step, we've got zeros in the first column. Now the second step is going to be to multiply on the left by Q2. And that's going to be done in such a way as to put zeros into column 2. Well, to do that, we're going to have to be careful. Remember, we're multiplying on the left, so we're going to recombine the rows. But we don't want to change anything. We don't want to combine the first row with all the rows below it, because that'll wreck the zeros that we've already put in. So we leave the first row alone. And then below that, we recombine the rows in such a way that, of course, recombining the zeros on the left doesn't do anything to them. But in the second column, things are designed to give us new zeros. And then in the third column, the numbers change, but not to anything special. And so you see how this proceeds. After we do one more multiplication with Q3 on the left, we want to have zeros in the third column below the diagonal, which means we're going to have to leave the first 2 rows alone. And then the last 3 rows are recombined. And in the third column, we put in the last zeros that we want. And what's left is what we would call the R matrix of the QR factorization. Then you finish the thing off by saying that, well, the product of orthogonal matrices is another orthogonal matrix, which we would call Q transpose. Multiply both sides on the left and use the fact that Q is an orthogonal matrix, and that gives us A equals QR. Right, because Q transpose is the identity on the left-hand side. Okay. So all that boils down to saying that we really want one basic operation, which is to say, in each stage when we multiplied by one of these QJ matrices, we took one column of numbers and we turned it into a non-zero followed by a bunch of zeros. So call that target column Z. So in the case of Q3, this was the target column here. Okay, in the case of Q1, this was the target column here. Okay, so it changes from one step to the next. But in any case, what we want to do is take that column, multiply by a P on the left, which is orthogonal, and then we put zeros below the diagonal, or in other words, below the first row of that vector Z. Now remember that orthogonal matrices can't change the 2 norm. So whatever the 2 norm of Z is, right, the 2 norm of PZ must be the same thing. That was a theorem we had about orthogonal matrices. And, you know, a matrix or a vector which has 2 norm, which is given, and which is non-zero only in the first element, well, all the first element has to be either positive norm Z2 or negative. The choice does matter a little bit, but here we're just going to take the positive one. Okay, so we want to design P so that PZ ends up to being this vector here. It's non-zero only in the first element. And we'll write that as Z plus another vector V, where V is the difference. So this is just a definition. Okay, so the picture that goes with this, if we imagine that we're working in 2 dimensions, we have some vector Z here that's given to us, and we want it to end up, after we multiply by P, we want it to end up on the positive x1 axis. The difference between these 2 vectors is what we call V. Okay. Now we can do a little geometric analysis here to suggest what the answer ought to be, and then use algebra to compute it. So you can imagine if we draw a mirror halfway in between these 2 points. Well, what do mirrors do? They reflect. Reflections don't change norms, and so our reflection is going to give us an orthogonal matrix. All right, and if we put the mirror right halfway in between these 2 vectors Z and PZ, then it does the right thing to the vector Z. So the idea behind the operation P, so P will mean reflect through this mirror. So whatever point I start with, x, px is the image on the other side. Okay, so that's the geometry, that's the picture. That's kind of the easy part. Now we have to figure out the algebra. Okay, so let's redraw it down here, but with less of the clutter. So here is our mirror. Okay, and then here is the vector x. Let's say the origin is here. Okay, the image point, well, we can find it by dropping down the perpendicular and reflecting through equally onto the other side. So that would be the vector px. That's where we want to end up. Now, remember that the mirror is perpendicular to this vector v that we defined earlier. So v is some vector going in this direction. So let's look at the vector. I'll draw it in purple here. Okay, call this vector w. Okay, so if we take x plus w, that puts us onto the mirror. All right, well, we can do some basic trigonometry here to say what is the length of w. Well, if we draw in the angle here as theta, then it's pretty clear that that's the length of x times the cosine of theta, because we have a right triangle. Now, how do we get theta? Well, theta is the angle between the vectors negative x and v. So we can do this by taking the inner product of those two vectors and dividing by the length of v. Right? The dot product is length x times length v times cosine theta. So that gives us the length of W, the direction of W, okay, it's a unit vector in the same direction as V. Okay, so altogether the vector W then, right, is negative, it's just the product of these two things. So negative X transpose V divided by norm V squared. So this is the length of W, the direction of W. So this thing here must be W. So X plus W gets us to the mirror. X plus 2W gets us to the point PX, right? So if we add W again, we get to PX. And so to get from X to its reflection, we add this vector here. So that gives us a formula for P times X for any X. And then if you're clever, you realize that you can change the order. This scalar here can be moved, and you can write P in terms of this outer product. So this gives us a formula for the actual projection, the actual orthogonal matrix. So you can check, I won't go through the algebra, but you can check that P transpose times P is in fact an identity matrix. So P is orthogonal. You can also check, I won't go through the derivation, that P times Z is the thing we set out to be. It's the norm of Z times E1. So this kind of matrix P is called a householder reflector. It's the basic unit of operation, the same way that row operations work in the Gaussian elimination algorithm. Okay, so that's an outline. Then what we do is we take, we know that if we take one Q after another and apply them on the left, we end up with the matrix R. As I said before, call this product of matrices here Q transpose, so Q transpose A is equal to R. Multiply by Q on the left of both sides, and then use the orthogonality to say that A is equal to QR. So in other words, if we can take this product of individual Q's, then you take the transpose and you end up with the Q of the factorization. Okay, so that's what I'm showing here. If we start with an identity matrix, of course, that doesn't change the product, right? So you start with an identity, you apply each of the householder steps to that identity matrix, and then that gives you the Q transpose, so at the end you transpose back. Here's the program that does it. It's a little different from the one that's presented for you in the book. It's a little better than the one in the book. I won't step through it bit by bit, but basically speaking, it follows the definitions I used above. So here's the Z, which is the target of the reflection in order to put in zeros. This is the same vector V that was defined above. Okay, we change things a little bit. We make the formulas a little easier by taking that V transpose V that's in the denominator. We set that equal to 1 by rescaling the V vector. So that's what the next step does. It's just a convenient step. And then all we have to do is going back, right? Anytime we want to apply the P to a known column of A or of Q, we use this formula here with the, we use this formula here. We just take the X, take this inner product, and multiply by 2V, subtract it off. So that's what this line is doing. It's taking the inner product of V with X times 2 times V, just doing it in a particular order, and subtracting that from the original X. At the end, you take the transpose of Q, and you get the QR factorization as a result. If you go through all the work, you find out how long this takes. Again, Again, m and n are different numbers, so you have to have an asymptotic term for each one. The highest order terms are 2mn squared, but you then subtract off a minus 2/3 n cubed in the limit.